We were gathered to explore the frontier of innovation in hydrogen production and storage. Your presence here signify a shared commitment to advancements of sustainable energy solution, and I extend my warmest welcome to each and every one of you. So we can't have a session without speakers, so please join me to extending a warm welcome to our estimated speakers for this session. Professor Hisham Ben Youssef from the UM6P University, Dr. Leonard Estevan from the Fraunhofer Institute, if I'm right, and Professor Ayoub Abdelkader Mikawi from Qadi Iyad University. So we are truly honored to have such distinguished speakers in our session. So please applaud our speakers. So in the realm of clean energy as sustainability, hydrogen has emerged as a key player with the potential to revolutionize our energy landscape. As a versatile and environmentally friendly energy carrier, hydrogen holds the promise of empowering the greener future. Central to the efficiency utilization of hydrogen are the catalysts and materials that drives its production and storage. So in this session, we'll be introduced to the most recent advancements and uses of catalysis and material innovation in the context of hydrogen production and storage. So with no more ado, I will let the floor to Mr. Leonard Estevan, a senior scientist from the Fraunhofer Institute for Interferential Engineering and Biotechnology. So, Mr. Leonard, the floor is yours.
Thank you very much for the kind introduction. So, ladies and gentlemen, it's my pleasure to be here again in Morocco for this great conference summit. I will keep it short. My talk is focused on catalytic processes for hydrogen conversion. I'm working at Fraunhofer IGB, which has 3 sites. The headquarters is located in Stuttgart, in Germany. And then there's another site located in Leuna. And the third and youngest site is located in Straubing, which is a very historic place because Joseph von Fraunhofer was born in Straubing, and that's why we have their Fraunhofer Institute branch now. As I said, our site is very new and sort of very modern, based on a modern concept. That means we have competences from biocatalysis, chemical catalysis, and electrocatalysis, and we are not only using these processes separately, but we also combine them in a sort of unique way, which is very important because we are doing process development. And as you move away from milligram scale to gram to kilogram scale, you need to have all the components within one building because it gets very complicated otherwise. So as I said, we are combining all these competences in order to convert biomass, water, nitrogen, CO2, and electricity into all these products that you see. And I highlighted the first 3 because these are relevant for the subject of this summit. You have heard this already multiple times today and also yesterday. Why is hydrogen all important? It is because it is of key importance in synthesis of fuels, of chemicals, of fertilizers, and basically everything that surrounds us. So that's why we started with CO2-based synthesis of methanol, one of the key intermediates for the chemical industry and also for synthesis of fuels. We caught up very fast with the state of the art. So as you can see, our third catalyst already approached in 90% the industrial catalyst. But more importantly, we pushed the boundaries of catalyst synthesis in a way that we converted the batch synthesis into continuous synthesis, which improves the yield per day by factor 2.5 to 3. That means you can almost triple the catalyst output with this synthesis, which, by the way, is the same. You don't have to add anything else. It's the same method, but we managed to optimize the production of the catalyst. Then we further integrated our activities towards process development. That means we combined CO2-based methanol synthesis with further conversion of the methanol, as you can see it here. We fermented the methanol into terpene, CO2-based terpene. But terpenes are not the only products. We can get also isoprene, lactic acid, polyhydroxybutyric acid, which is a polymer, or terpenoids in general. And as you can see on this picture, the market price of all these compounds are way higher than the methanol itself. And this is the important factor here. When going from hydrogen, which we have seen price estimates for that, and we see that some of the projects are already economically viable, but lots of them still not. But if we have a process to convert that hydrogen into end products, which have a way higher market price, that would push the economics of the entire process chain into a more favorable one. That means if you would have only methanol synthesis, that process would be cash negative probably for a very long time. But if we produce all these chemicals, that turns the process into cash positive, that means the net present value will become positive after some years. So some project examples. This is the power to methanol project that run in Germany with lots of high profile companies and institutes. Here, the goal was to do process development for the CO2-based methanol synthesis with electrolytic hydrogen, of course, using a CO2 from second and first generation bioethanol plants. One of them is in Zeitz, Germany. The other is right next to us in Straubing. We made process development, and we also supported the decision-making for building actually such a plant. Another example of a project is collaboration with Morocco right here. We made a techno-economic feasibility study for OCP and IRESAN as main stakeholders. In 2019, we presented the results of the study, and since then the cooperation is still going on. As you can see, we had a site visit at OCP with the Green Dream Team, and the pilot plant construction is ongoing with the colleagues from here, from Morocco. So a little bit of outlook into what we are planning to do. As I showed, from catalyst development, we made a step further into process development, but now we take a step towards electrolysis technologies as well in the next future. And there we will address a few questions about how to decrease CapEx and OpEx. And that can be achieved by development of anode and cathode. Membrane development is also something very important. And it's not only because of, or actually not at all because of academic interest, but because of regulatory requirement to use fluorine-free membranes. This is something very important. And going on further, also the electrolyzer design is something very important. And as you can see here, I put the three dimensions which can bring towards decreasing CapEx and OpEx. One of them is substituting platinum group metals and precious metals, for that matter, from the electrolyzers. But on the other hand, we also have to develop these electrocatalysts in a way that they have comparable performance and also comparable lifetime to existing anode and cathode materials. So with that, I come to the end of my presentation, and I would thank you for your kind attention. And yeah.
Thank you so much, Dr. Leonard. So now let's move to the material development for the next generation water catalyzers with Professor Ben Youssef.
Okay. Thank you very much. I think it was a nice pre-introduction from my colleague Leonard. I think the membrane or the, let's say, diaphragm is really the heart of the system. And then I would like just to just for the introduction, coming from the Mohammed VI Polytechnic University, I'm leading the high throughput multidisciplinary research laboratory, and also I am co-directing the Applied Chemistry and Engineering Research Center of Excellence at the same place. We are really keen to develop different, let's say, fields, among them catalysts and separation process, energy conversion, and also storage, materials developments, and other parts. Just to make the context, what we are doing at Mohammed VI Polytechnic University, which was, let's say, it's a young university, started or inaugurated by His Majesty the King in 2017. And in this context, we are really trying to position ourselves, especially for specific objectives related to the thematic of the hydrogen as a career or as also commodity, building test facilities, which we are commissioning now, also trying to accelerate the development in different fields of materials research. And also we have to form people. That means tomorrow, if we are going to this, let's say, field, and we want to bet on it, we have to form a lot of people, and then we have to be there when the necessity will acquire that. I like always these slides, just to mention that we are really coming to school back again from 1800, and I like the statement from Jules Verne that he was saying water is the call of the future in one of his books, and it's damn, he's right. For the moment, it's really the point, which makes the point of also related to materials development in the field for production of hydrogen. When we are talking about this, normally I have in mind that we are talking about scarcity of materials, metals, noble metals, but always we are forgetting the water. That becomes really a necessity to take care of it, especially also in Morocco. Water is for drinking first, and then afterwards we can transform it to hydrogen. Just if I look to the system, all the systems really, it's the normal electrochemical cells, and we have we are talking, Lena talked about the electrodes at the end, cathodes, anodes, which we have catalysts. And the heart of the system, as I mentioned, is these membranes, depending if we are talking about proton exchange membranes, electrolyzers, or you are talking about alkaline electrolyzers, you have a diaphragm. And then just to put as you mentioned by Leonard, the importance of this heart of the system. This means it has some functionalities. It needs to transport ions, it needs to be insulator, it needs also to not leave or not have crossover of gases. This means hydrogen has to stay in his way, oxygen has to stay in the other way, other side. And then of course we have to have materials which is stable, to have chemical, electrochemical, thermal, also mechanical stability. And especially this is to have long life or durability for the system. You cannot have technology which you have to stop every 20,000 hours and then you are bidding for millions and millions of dollars to change things. I wanted just to go back from this discussion this morning or also yesterday that people are talking about megawatt and gigawatt. And then I'm thinking, let's say, go back to the micro scale, that we are talking about materials. We're not about the stack, but we are talking about real materials. And in that context, of course, the alkaline is really going ahead. It's already well established for decades. And also based on the directions to renewable energy, we have to think of new, let's say, systems which can be adapted with different commodities. And then for that, if we think of the next generation of these alkaline electrolyzers, we have also to think of having differential pressure, high efficiency, and also enhanced rate capability. And of course, keeping in mind the lifetime, the durability, as I mentioned, the cost effectiveness, and also other parts. Just if we look to the normal, the well-established porous diaphragms, we have, as I mentioned, the typical micrometers range is like smaller, let's say, we call it porous diaphragms, which is based on polyarylene ether sulfone. And then, of course, we have the use of ceramic zirconia to have this, let's say, you are reducing the crossover of the gases. And also we have other materials, polysulfone, polyphenol sulfides, which are also used in the form of fibers for this kind of materials. Now, the other part, which is still in progress, we are talking a lot about anion exchange membranes. And in this case, we have membranes and you have polymer phase, and then you can think about the quaternary ammonium, let's say, groups, which is functionalized. And then you can see it here that you have also these ionic, let's say, groups, which are helping the oxide in that sense to move, to be transported through these membranes. And this technology also is quite promising, but also the durability is still not there for a lot of systems. I just give here some tests which were performed examples in the stack level with some, let's say, polycarbazoles, and also you have some other materials related to polyethylene benzimidazole, which are well established. The other examples of technology, which is also part of this, let's say, separator technology development for alkaline, let's say, electrolyzers, we have the ion solvite polymer membranes. This term is coming from the battery side, because normally we are talking about solvatation for solid state batteries, the next generation. And this is just taken from this concept and applied here, even though it's, we are talking about aqueous here, aqueous systems. And just here, two examples also which are promising based on this polymidazole. This polymer is already well established for phosphoric acid transport for the fuel cells and other, let's say, field. When we are talking about fuel cell, we are talking about the back reactions. That means we are going electrolysis in one side, and you are using electricity to produce hydrogens, and you are producing electricity from the hydrogen you are already having by fuel cells. Just here a summary of these three examples I showed just now, and this just to show the most important part is the safety, and then all this part related to the hydrogen level in the oxygen, let's say, within the membranes. And then based on this, I want just to summarize this kind of technologies to really make that still the porous diaphragms, then let's say the traditional alkaline electrolyzers are still having high durability in comparison of all the new technology which are now, let's say, being developed. And also the technology is mature to that it will have several years ahead of all the other part. That means there is quite a big need to develop really materials, membranes, separators for the next generation. We are talking about proton exchange. This is a part which has to be done because we have the possibility to play with the pressure. And this is, and also the current densities that you can really have hand on the produced or the load you are having. And this can be done with really having a close look in different parts, materials, structures, morphology. And with that, I want just to finish with some of the examples we are happy to share. The examples for let's say called the Valley of Hydrogen, which was accepted in the H 2020 with the colleagues from Turkey, and the kickoff will be in December 2023. And with that, I think I will thank you.
Thank you for the nice talk, Professor Ben Youssef. So now we will move to the novel nanostructured heterogeneous catalysis, hydrogen transfer, and dehydrogenation reaction with Professor Ayoub Abdelkader Mkawi.
Thank you. So, thank you. First of all, I am Ayoub Abdelkader Mkawi, Assistant Professor in Organic and Catalytic Chemistry from Halle-Wittenberg. Taking into consideration the allocated time, I will give an overview about our works on novel nanostructured heterogeneous catalysts towards hydrogen transfer and dehydrogenation reaction. So first of all, let me introduce for some who are not familiar with catalysis, what is catalysis. So catalysis is a very demanded field, both industrially and in academic research, with the interest, sorry, maybe it's not working there. So with the interest of reducing reaction time, improving the selectivity and the specificity of a catalyst to another. It is also an important tool in circular economy and sustainable development because it represents one of the 12 principles of green chemistry. By definition, catalyst is a substance, solid, liquid, or gas which reduce the chemical reaction reduce the chemical reaction time by decreasing its activation energy. In catalysis, we found three major types of catalysis: homogeneous, heterogeneous, and enzymatic catalysis. In this, today we will focus on heterogeneous catalysis. Why heterogeneous catalysis? Because heterogeneous catalysis is easy separable, thermally stable, solvent-free. We can use it in a solvent-free condition and easy to regenerate. In heterogeneous catalysis, we have two types of catalysts: bulk catalysts or supported catalyst, where we can disperse or decorate nanoparticles on a support because it is important for the catalytic reaction that occurs on the surface of the solid. So today I will give some of our objectives about novel nanostructured heterogeneous catalysts and towards hydrogen transfer and dehydrogenation reaction. So first, the implementation of simple and ecological process for the preparation of novel metal nanoparticles as pristine or anchored on to polymers or dispersed on materials with the focus on valorization of bio and waste materials. Also, advanced characterization of the developed material nanoparticles based catalytic systems, and the study of the catalytic activity of the prepared nanocatalysts in hydrogen transfer and dehydrogenation reactions. First, here I will give example of some of the developed catalytic system. First, we had focused on the biosynthesis of nanoparticles in a MIGE grant project financed by Italian Ministry of Foreign Affairs. So we have studied the carboxymethyl cellulose as one of the major abundant biopolymer and polysaccharide in nature, and core metal nanoparticles. Here we have prepared palladium nanoparticles, and we have studied the coordination mode of the catalyst through structural characterization, as well as some microstructural and nanostructural study. We have, through FISM study, we have demonstrated that the nanocolloids are well dispersed, about 200 nanometers, and well stabilized. And from the CHIM study, we can see that the nanocolloids are well dispersed and stabilizing nanoparticles, palladium nanoparticles. We can see above that palladium nanoparticles were about 2 to 10 nanometers in size. So the developed nanocolloids were used to prepare some supported catalysts, especially mono and bimetallic nanoparticles decorated mesoporous natural phosphate. So we have studied in the beginning the palladium developed palladium nanocolloid and their deposition on natural phosphate in 1, 5, and 10% per weight. And the optimized condition were used to prepare other mono and bimetallic nanoparticles supported natural phosphate, as for example, cobalt silver nanoparticles. And we have demonstrated through the microscopic, nanoscopic, and structural studies, especially XPS, the synergy between both metals and the effect of cobalt oxide on silver. We have different silver oxidation, and it's depend on the preparation method. So for the catalytic applications, first we have studied the hydrogen transfer reaction, and we have studied the capacity of the developed nanocatalytic system on the catalytic generation of hydrogen from borohydride. And we have studied a benchmarking catalyst test that it's well known for the test of nanoparticles and their ability and their catalytic activity in the reduction of nitro compound with which they are considered as organic pollutants with some harmful results on the nature and the flow. So, and for to prepare significant interested chemical products in chemical industry as amino compound and important intermediate in organic synthesis. The second application, which is Leonard, my co-panelist, Dr. Leonard, gave some talk about some results about biomass valorization. In our laboratory, we have worked on the valorization of citrus oil compounds, which is a renewable raw materials as abundant natural olefins or natural terpenic olefins. And it is about 70% of the essential oil of Moroccan Citrus atlantica, and it is a potential precursor for dehydrogenation. So we have studied its dehydrogenation through the development of a new catalytic system or novel catalytic systems compared to only two heterogeneous catalytic system in literature, the palladium-supported carbon and the Rani nickel. And the dehydrogenated compound, Arili Machalen, it's only 0.5% of the essential oil of Moroccan Citrus atlantica, and it is important intermediate in the synthesis of perfumes, and is considered as pheromone component produced by insects, and it's antibacterial with the antibacterial activity and widely used in pharmaceutical industry. So to conclude, we have seen an overview about some works in the biosynthesis of CMC and core metal nanoparticles, and also the preparation, the using of this nanocolloid in the preparation of novel materials decoration nanoparticles and the characterization, some of the characterization study. In the catalytic application, we have seen the catalytic hydrogenation of nitro compounds, catalytic dehydrogenation of natural olefins, with and the developed catalytic system shows high recyclability with good thermal and structural stability. In our perspective, we are trying to develop more this study and also to design novel magnetic nanostructured catalysts for a better and easier recyclability. Also to develop some catalytic power to X systems such as CO2 electrochemical reduction reaction, CO2RR, and the capacity of generation and transfer hydrogen, as well as some cascade reaction about dehydrogenation and hydrogenation of some substrates. I would like, before finishing, to thank all our national and international collaborators, as well as some financing projects, such as Alumni Farnesina, project financed by the Ministry of Foreign Affairs, and some collaborative work financed by CNRC and TÜBİTAK with the Turkish collaborators, as well as my research stays in University of Granada, Spain. And thank you for your attention.
Thank you, Professor Mkawi, for your presentation, and also thank you, Professor Leonard and Professor Ben Youssef. I will take the advantage of being the chairwoman of this session to ask some questions to each one of you. I will start with you, Professor Ben Youssef. So, in your personal point of view, what are the advantages and disadvantages of different methods of hydrogen production and storage?
Thank you for the question. I think the relation, let's say, between the different productions parts are always related to the cost, the efficiency, let's say the purity of the gas or the hydrogen you will get, and also I would say 60% is based on materials. Now, if we look for what I showed just for the alkaline, see that there is no use of, let's say, noble materials. This is already a good part, let's say. And then if we think of the next generation, or now they are talking about proton exchange membranes, electrolyzers, which are assumed to be the next generations, which are more modular and so on. But we need to have noble materials. We need to have platinum, which we don't have, especially in Morocco. We have to think of also the systems, the separators or the membranes. It means there's always, let's say, equalizing system that you have to take let's say the challenge to say, okay, I will take this with its drawbacks and try to increase or improve this drawbacks, let's say, existing. But definitely the alkaline is still ahead. It's quite durable. It's really, let's say, forefront the other technologies, let's say.
So, Professor Mkawi, for you, what are the main challenges and opportunities related to the development of innovative catalysis and materials for hydrogen production and storage?
Okay. For the development of materials or catalysts for hydrogen production and storage, if we can see in the literature, most of the metals or the catalytic systems are widely studied and known. The optimization or looking for a synergy or to improve the stability, thermal stability, or the electronic system in the catalysis process. It's one of the major, if we can say, topic to study, because as I have said in the beginning, so most of the catalytic system are widely known. So we have to improve it through doping or adding some other metals or some substance that will improve the catalytic capacity and the regeneration, the recycling of the catalyst or the reusing of the catalyst. Thank you.
Thank you so much. And for you, Professor Leonard, how to ensure that the durability, safety, and cost effectiveness of hydrogen production and storage technology?
Yeah, thanks a lot. So this is indeed a very complex question about the durability. Of course, we would have to find catalyst systems, electrocatalysts that can perform on long term in a comparable manner with methods that we have now in existing electrolyzers. That means nickel-based materials in alkaline electrolyzers, platinum group metals for alkaline. This is a quite challenging task, and mostly for the anode part, because there we have the largest problems. Anodes get corroded very easily, and substituting platinum group metals is not an easy task because of the corrosion problem. On the other hand, we have also, as we talked about it, to improve the membranes, especially all these new membrane systems have to withstand all these conditions for 80,000 hours or more. So this is something that is all a cost driver, probably a small percentage in the entire cost, but this is something that still needs to be addressed in R&D projects. And yeah, we are very happy to cooperate with all of you. There are a number of binational projects and also EU Horizon 2020, or what comes now Horizon Europe projects for which Morocco is Morocco can join as partner country. So we are very happy to cooperate with all of you in order to tackle all these questions about affordability and stability of electrolyzer systems.
So, dear audience, if you have any question, please don't hesitate to approach our remarkable speakers at the coffee break. So, to conclude, as we draw the certain on this enlightening session, it's clear that hydrogen is supposed to be a game changer in the quest of clean and sustainable energy. The innovative strides showcased today undercross the remarkable progress being made in hydrogen production and storage. So thank you for being part of this session.